Yet again, I have the honor to introduce to you all our next lecturer. The second lecture of the day is titled Cosmology with Baryonic Acoustic Oscillations and is presented by Dr. Hee-Jong Seo. Dr. Seo is an associate professor at Ohio University with a primary research focus on enhancing the accuracy and precision of clustering measurements obtained from large-scale galaxy surveys. Dr. Seo's key involvement in Dark Energy Spectroscopic Instrument survey experiments includes, but not limited to, serving as a co-chair of DESI Galaxy Quasar Clustering Science Working Group, and then as a convener of the DESI Year 1 Baryon Acoustic Oscillation Key Project. Dr. Seo has contributed to prominent large-scale galaxy surveys, such as the Baryon Oscillation Spectroscopic Survey, BOSS, Extended BOSS, and is currently involved in the ongoing Dark Energy Spectroscopic Survey and Roman Space Telescope Galaxy Redshift Survey.
So for my talk, I will focus on more intuitive, simplified summary of the BAO method with some technical details, but all these can be connected to the theoretical models that Stephen presented today. Okay, so outline of my talk, and I first like to start with the physics of the BAO, which is introduction to the BAO. And then I like to talk about the BAO as a standard ruler, a very simple guide to the method. And then cosmology, what kind of cosmology constraints we can derive from the BAO measurements. And if time permits, I would like to also give a few slides of summarizing the history of the BAO measurements, including DESI. So physics of BAO. Okay, so probably many of you are already aware, but let me just repeat from the beginning. So Baryon acoustic oscillations are primordial sound waves that propagated in the very early universe. So in the early universe, the universe was hot and dense, and photons and baryons were tightly coupled by Thomson scattering. And imagining, if you imagine a quantum fluctuation in any random location of the universe, because it's not only overdense in dark matter, baryons, it's also overdense in photons, it will initiate a pressure wave, a spherical sound waves. So here, the central peak is due to dark matter, and this propagating wave is the baryon and photon fluid. And the wave propagates at really great speed, a speed close to the speed of the light. But while this wave propagates, the universe expands and cools down. And around the epoch of recombination, which is 400,000 years after the Big Bang, and also when the universe was about 1,000 times smaller than today, the universe became more or less suddenly became optically thin to Thomson scattering. So as a result, baryons decouple from photons. Because the photon has been providing this pressure for the pressure wave, the sound speed of the gas suddenly decreases. So at this epoch, the wave that has been propagating suddenly almost stops, immediately stops. So at the end, we are left with a spherical peak with the size at the distance that the wave has traveled before the recombination. So that's called the sound horizon scale. And that's our fundamental scale, that the physical scale that we, for the BAO analysis. The scale today is 150 megaparsec, or it expands with the expansion. So at 0,000, it must have been 150 kiloparsec. So so this feature left its imprint in the distribution of the freed photons, which shows up as this oscillatory feature in the power spectrum of the CMB data. And for baryons, so baryons now freely can fall into the potential well of the common potential well with the dark matter. So they will contribute to the structural growth. The central peak due to dark matter and the spherical peak to the baryons, they can happen anywhere in the universe. So the real universe is many random superpositions of such the central and spherical peaks. And the galaxies will form where there are more, tend to form where there are more dark matter. And with this Baryon Acoustic Oscillations, which is co-expanding with the expansion of the universe, the idea is we can measure the size of the feature and will tell us the distance to the various look-back time, and that encodes the expansion history of the universe. Okay, so let me give just one more slide, actually a few more slides about the standard ruler test. The premise of the standard ruler test is that we have a feature with a known physical scale or a feature with a physical scale that doesn't change. The BAO is a spherical peak, means it's a 3-dimension. So we can do the standard ruler test in 3 dimensions, like standard candle with a supernova. It can't do, there's no 3-dimensional information there, but here for BAO standard ruler test, we can actually derive 2 distance measurements. By looking at how small it appears along the transverse direction, which is just delta theta we measure, this can be connected to the true physical scale through the angular diameter distance. And by looking at how small it appears along the line of sight, which is redshift extent, that can be, that can be related to the true physical scale delta R through Hubble parameter. So by knowing what the true size, in this case, the sound horizon scale at recombination, we can measure angular diameter distance and Hubble parameter separately. So that's called the standard ruler test. And as we are aware, if you take time derivative of Hubble parameter, and if you take second time derivative of the angular diameter distance, we can derive the expansion rate, which can tell us the dark energy density as a function of time. So although we measure the transverse and line of sight direction, it's done simultaneously, but the dimension, the 2 directions are different. When we measure, we have no consideration in terms of internal consistency. But if you look, the angular diameter distance is actually integration of inverse Hubble parameter. So the result we get is bound to have internal consistency. So this additional internal consistency check is allowed with the BAO analysis. Okay, so we want to detect the BAO feature from the galaxy surveys. From the Stevens talk, we already know that we are going to use a power spectrum and correlation function. But let's just back up from there. Let's think about the feature in this distribution of the galaxies. So I want to detect the BAO feature from this large 3-dimensional map of the universe. So the measurements is array, deck, and redshift. It's very hard to define a shape, whether the shape looks like a spherical peak, this spherical shape, or different shape in this coordinate system. So for practical purpose, we want to work this in the physical space. So we want to convert that to the XYZ coordinates and work on and analyze the BAO. For that, we have to assume some reference cosmology. We have very good knowledge about what reference cosmology to use, such as Planck 2018, which would be pretty accurate enough. So we use reference cosmology, and given the reference cosmology, if this cosmology is correct, the BAO peak should appear very spherical. And also, based on the reference cosmology, we know what should be the sound horizon scale in the reference. So now we do measure, observe the BAO. Let's say this is observer, and we are going to measure. So if the BAO appears along the transverse direction, appears bigger than what we expected, which is possible because we don't know the true distance scales we should have used. So that means the observed size of the BAO appears greater than the reference size of the BAO in terms of angular scale. So what does that mean? That means the combination of RD, sound horizon scale, true sound horizon scale, and the distance is relative to what we have assumed is greater than 1 in this specific case. It could be small as well. So we parameterized this as a BAO parameter, which is 1 over alpha perpendicular. So we are measuring how small the BAO appears across the line of sight by just alpha perpendicular. Likewise, I can do the same thing along the line of sight. Again, I can measure how small it appears along the line of sight, which tells me in this specific case, the size along the line of sight is bigger than what I expected based on the reference cosmology. That means the combination of RD times H, the true quantity is greater than the combination that I used based on the reference cosmology, which is perfectly fine. We measure how big it appears, and therefore, because we know what reference RD and H we used, we can derive the true RD times H. So note that we can only get the combination of RD times distance in this standard ruler test. So this is parameterized as alpha parallel. So this is one set of bases we often use. And for the later purpose, we often say this Hubble distance, which is just inverse of a Hubble parameter. We can also use the other basis which we use really often, which is a overall size of the BAO. So it's a spherically averaged BAO size. And that parameterizes another combination of the distance called isotropic distance dV, which is the geometric mean of dm and h, and combination of RD over dV. So that's what we so this is really observable. And the orthogonal set to alpha iso is the looking at the anisotropy of the BAO, whether it appears oblate and prolate. So we are aware, right, that based on cosmological principle, the BAO should appear isotropic, right? Why would it appear anisotropic? Stephen's talk, you probably heard about redshift space distortions, which can introduce anisotropic clustering as a function of line of sight. But that cannot change. So they can change amplitude of power spectrum, but that the redshift space distortions cannot introduce the anisotropy to the shape of the BAO. So BAO is really anchoring the geometric effect. So the reason why the BAO may appear anisotropic is because we have assumed incorrect combination of distance and Hubble parameter. So again, this tells us the true combination of distance and Hubble parameter. So this is called Alcock-Paczynski BAO parameter. So sometimes, so because AP, as you can see, in order to say something about oblate and prolate, we really have to compare modes, transverse versus along the line of sight. So the deriving AP parameter requires more signal to noise of the data. So in the case when we do not have a high signal to noise BAO, we usually focus only the isotropic BAO measurements while just dropping the AP, so setting AP to be 1. Okay, so the premise of the standard ruler test is that we have to know the true physical size of the BAO. As I said earlier, the true physical size is the sound horizon scale in this case. The sound horizon scale is the distance the wave has traveled. Therefore, there should be integration of the sound speed times the time of the universe until the decoupling epoch. The speed of this sound wave depends on the baryon to photon density, where here R is baryon to photon density, and the time between in the beginning to the decoupling time depends on the matter density and photon density. And we can derive photon density from the same temperature. Therefore, if we know the baryon density and matter density, we can actually precisely determine the sound horizon scale. So how can we determine baryon and matter density? As many of you are aware, the shape, these oscillatory features of the CMB is sensitive to the baryon and matter density, and therefore CMB actually provides the independent calibration of the sound horizon scale. One thing to note is because CMB itself has Baryon acoustic oscillations, it also tells us what is observed angular size of the BAO, the ancient BAO at Z of 1000. So CMB provides, for the purpose of the BAO, provides the sound horizon scale and the very early angular size of the BAO. Okay, so as Stephen has already introduced, the BAO peak is a really weak feature. So we, of course, cannot just observe. And also this is a statistical feature. So we have to really stack that on it or over every location of the universe. So we conduct a standard ruler test using correlation functions and power spectrum. So I will switch between correlation function and power spectrum during this talk. So in correlation function space, this power, this is a log plot. This power corresponds to the imprint of dark matter clustering, and this corresponds to the Baryon acoustic peak, which is broadened by a imperfect coupling between photon and baryon at the epoch decoupling. So this is really intrinsic width of the intrinsic sharpness, the maximum sharpness we can achieve for the BAO, which is about 8 megaparsec per H. So when we work with the correlation function, we say configuration space. When you work in power spectrum, we say Fourier space analysis. A single peak in one space is a series of oscillations in the conjugate space. So the standard ruler test is really trying to measure the location of this peak and also the location of these rigors in the power spectrum. So again, the premise of the standard ruler test is we know the size of the ruler, but as Stephen as Stephen explained, our ruler has been blurred and shrinking. You saw this figure from Stephen's lecture. So the BAO peak has been damped due to the structural growth, and as he mentioned, actually has been shrinking. So we actually have a little bit of problem in a sense that the accuracy degrades with the decreasing redshift, and the precision also degrades as well due to the standard ruler test. To summarize what this nonlinear effect would be like, so here I'm showing the real space, meaning there is no the redshift space distortions. And if you look at the black, which is a linear BAO feature, versus the dashed blue, which is a nonlinear BAO feature, the broadening can be described as a Gaussian convolution, and Stephen mentioned how we can derive the Gaussian convolution or Gaussian damping for this effect. So in the configuration space, it can be expressed as a Gaussian convolution, and of course, if you Fourier transform, that becomes Gaussian damping. So you see that the BAO peaks, starting from the small scales, actually increasingly damped to the larger scales as the redshift increases. Because this is due to large-scale bulk flow, which increases with the growth factor, the damping is proportional to the growth factor, and we can reasonably predict what the growth factor would be like within a few percent or within 10%. So the damping of the BAO is reasonably predictable. So we have a pretty good understanding how the BAO will evolve. At the Z of 0, it is about 8 megaparsec of additional damping in real space, in addition to the Silk damping. Again, you see this figure, so the BAO can be described as the linear BAO times the exponential damping. This is a really good description of low redshift BAO peak. Redshift space distortions, and now you can see the blue dashed line is further damped because the redshift space distortions makes particles displaced along the line of sight due to the Doppler shift. There seems to be additional, right? They will appear such that there is additional displacement along the line of sight. So there's additional damping by 1 plus F, where F corresponds to the F that Stephen showed in his talk. Okay, so now our rigor can be described, BAO can be described as linear BAO feature times damping. We call this a propagator because that describes the cross correlation between linear and the final field. And our propagator can be written in a way that has a two damping scale across the line of sight and along the line of sight. So there is a structural growth effect, redshift space distortion hertz along the line of sight. But now we have another effect, such as a galaxy bias. Well, it turns out that galaxy bias does not add much damping. It is about order of 1 megaparsec. So the bottom line, we have a pretty good understanding of how the PAO gets damped, as well as how much it is going to get shifted. So you have seen a really impressive, the derivation of perturbation theories from the Stevens talk. But what's good for BAO is, for our purpose, we can just write down our observable in this in a really simple form. So our observable, we can write down as a linear power spectrum that contains the BAO peak that has been damped with a propagator. This is 1, means we have all the linear BAO information in our data set. So this describes damping of the BAO, and therefore this governs the signal to noise ratio of the standard ruler test. So this is responsible for the errors of the BAO measurements. So this governs the precision of the standard ruler test. Now the rest of that, which doesn't directly include the initial BAO feature, we call this mode coupling terms, and that happened to have a very small off-phase oscillatory feature. So this is the term that generates nonlinear shift to the BAO measurement. So this is responsible for degrading the accuracy of the test. The amount of nonlinear shift is, again, from Stevens' talk, this is a higher order term from the mode coupling. So this is actually proportional to the growth factor squared. So as a function of redshift, the dotted line shows growth factor squared. And if we use the simulation, we can actually show that indeed nonlinear shift is following this dependence. Now with the redshift space distortions, there is an additional shift along the line of sight. And galaxy bias adds a lot more complication here because the bias tracers have a different amount of contribution from different bias, higher order bias terms. The shifts in the bias tracer therefore depends on the nature of a galaxy bias. So this plot is taken from Steven and Kullan's 2024 paper for DEGI. So please take a look at this paper. It has an extensive review on the BAO theoretical systematics. So as you can see in this plot, with RST and structural growth with galaxy bias, there are all different scenarios. But again, if you look at this graph, the transverse direction, the maximum in the worst case is still 0.5%. Along the line of sight, the worst case scenario, at least studied here, is 1%. So when we are worried about nonlinear evolution of a standard ruler, it's just still less than 1%. It's a small effect. Of course, we want to get rid of this, despite it being small. So let me now move on to the reconstruction part. Any questions so far? Okay. I will just move on then. Okay, so this is a cartoon way to show. So these two particles are particles that are displaced by 150 megaparsec in the initial time. So these makes the BAO peak in the initial time. And due to the structural growth, these particle displaces as they are moving toward just following the gravitational flow and moving toward overdensity regions, surrounding regions. And overdensity can happen in anywhere. So this generates a dispersions around the initial location, which can be, which is the reason why BAO is being damped. With the Doppler shift, the particles appear displaced additionally by additional amount along the line of sight, and therefore displacement from the original location appears even bigger with the RST, which is the reason why we have a greater damping along the line of sight. The density field reconstruction is tackling, so understanding that the degradation in the BAO is due to mainly large-scale bulk flow, and that this large-scale bulk flow is, of course, due to the gravitational, due to the gravity. We can describe at least for the linear order, because it's a large-scale effect, we can describe this effect just by using a simple continuity equation. So the displacement is responsible for the observed distribution of matter from the initially uniform distribution of the matter. So we can write down the continuity equation. And of course, what we do not observe dark matter in today. So dark matter density can be traced by galaxy divided by a reasonable estimate of a linear bias. So now if you describe what we observe today as a large-scale continuity equation with a large-scale displacement field, the question is, if we can undo such a large-scale displacement field, whether we can recover the nonlinear, the BAO from the various nonlinear effects. So the method applies this reverse continuity equation. So based on observed galaxy field, we divide it by the linear bias. And because a small scale galaxy field is, of course, subject to shot noise and it's subject to greater nonlinearity, for which this simple continuity equation may not work, we apply a smoothing kernel. Usually it's exponential damping, although it doesn't need to be. And we apply the smoothing kernel and apply this reverse continuity equation. So once we derive the estimated displacement field, the negative displacement field, we undo this, move the particles back by this negative displacement. So it actually comes in several steps. Usually when I give a talk, I only talk about the first step and then it just skips, but let me just add the second and third step. So we displace the galaxies based on this in reverse, the negative displacement field. And this, if we are successful, of course, this will bring the galaxies to close to the original position. So that removes much of nonlinearity from the field. That's great. But the only problem is, if the reconstruction is perfect, we are going to move all the galaxies back to its original initial location. So, but in that case, it would be uniform field. We lose all the power, zero power. So it's not what we want, right? We do want a large scale information. We want to have the large scale information. So we actually do the second step. We prepare a uniform field and displace the uniform field or random field by the same amount. So that adds back the large scale information back to the field. So that's called, let's say, S. So the reconstructed field is really the difference between the two. It's a difference instead of plus because we actually use a negative displacement field. So we remove nonlinearity and recover small scale information by displacing galaxies. And we add the linear large scale information by displacing a uniform field. And the reconstructed field is the combination of the two. Okay, yes, this is how this in cartoon will appear. The BAO will, as a result of this reconstruction, the BAO peak is it's substantially being sharpened, and as well as it removes the nonlinear shift. Okay, so so this is how the propagator. So I sometimes write this as D, sometimes C, and sometimes, but it's all propagator. So this is a propagator as a function of K, showing how the different components that enter the reconstruction really looks like. So here, if the propagator is 1, it means it's pure. It has all linear BAO feature intact in the later reconstructed field. Dashed line shows the exponential damping of the BAO feature before recombination, actually, before reconstruction. Now, solid line shows the damping after reconstruction. So you see the damping scale has been greatly reduced. This is not the simulation data, but this is based on perturbation theory that is trying to explain what is actually happens in reconstruction. So now if you look at the component, the reconstructed density field is the displaced galaxy minus displaced random field. And if I make a power spectrum, this is a combination of the power of the displaced galaxies and power of the displaced randoms, the cross term. And you see that the displaced galaxies brings back the small scale information, and displaced randoms adds back the large scale information, and cross term filling in between. So it's really the two fields coming together to recover the BAO feature from the nonlinear effect. As a result, the reconstructed field is better correlated with the linear field. And although you can see here that shift in the BAO is almost vanishes due to the reduced nonlinearity in the field. This is one of the examples from CMAS in 2017, just showing how reconstruction sharpens the BAO peak in the correlation function and in the rigors in the power spectrum. And this one shows, the reconstruction tested on the marks, and this is a precision before reconstruction and precision after reconstruction. And dashed line means no change. So you see most of the points are below the dashed lines, meaning the reconstruction really significantly improves the precision. And one thing to note is this is really statistical, meaning if you have one survey, when you conducted reconstruction, it is possible that you may not gain much from reconstruction, especially if the survey is not really high signal noise survey. There is random dispersion, but ensemble average would be improved by reconstruction. The nonlinear shift after reconstruction falls almost below 0.1%. So it becomes really, we are recovering the robustness of the standard ruler with the help of density field reconstruction. So what are good things can happen other than just the sharpening the BAO peak after reconstruction? It has other interesting features. After reconstruction, it has been shown that the covariance is more Gaussian. This higher order clustering, bispectrum, trispectrum contribution reduces after reconstruction. So also the BAO analysis is fairly stable against covariances. As a result, it's a Gaussian covariance matrix becomes a good match. It's good enough approximation for the BAO analysis. So that means the reconstruction not only increases the signal by sharpening, but also decreases noise by making the covariance matrix more Gaussian. So here, this is a plot from Voigtler et al. 2017. Before reconstruction, you see a lot of off-diagonal elements between different Ks. And after reconstruction, you see they are all becoming much more diagonal. And also, what's not obvious maybe because it reduces the nonlinear effect, the shape of the clustering resembles more to the linear shape here before reconstruction and after reconstruction due to the reduced mode coupling. Of course, once we add the RST, it kind of becomes a little bit much more complicated than just this simple statement. Okay, so let me pause here for a few minutes in case people have a question about this.
I don't see any question in the chat.
Okay. All right.
Maybe I have a question on the reconstruction.
Well,
So for the reconstruction, you need to assume a given model for the growth rate, right?
That's right. No. You mean for the RST or for
When you, because, okay, if I understand correctly, when you perform reconstruction, you will like move backward the galaxy to amplify the BAO signal, right?
Right. So we don't assume growth rate.
So it's not assuming velocities, right?
So no, we are for without forgetting about RST, what we assume is a linear bias for the tracer because we want to connect the displacement field to the matter distribution. Now, if I want to undo the reconstruction, sorry, if I want to undo the RST effect, the additional the seemingly displacement due to RST, we indeed assume a reasonable the F factor to account for the additional velocity amount. Is that what you're talking about?
I mean, like like at some point you need to evaluate the displacement field, right?
Yes.
So for evaluating the displacement field, at some point you should assume like, I don't know. I thought you will assume the growth rate at the effective redshift or something like this.
Oh yeah, yes. Sorry, I misnosed. I thought you said growth factor. So we do assume F in order to reconstruction to undo the RST.
Okay.
But that is not it. But we can include what is the growth factor we included, the growth rate we included to undo the RST in the modeling of the reconstruction. Because we exactly know how much we added there.
Okay.
Are you asking?
Yeah.
Depends.
I was thinking like how this like would change if you like how this can introduce any bias if like you assuming a wrong displacement field basically.
Oh yes, certainly. If you rather than bias, I would say more greater effect is the efficiency. If we use really incorrect bias or very incorrect growth rate to undo the RST, it's likely that our reconstruction is not optimal because our displacement is either overestimated and underestimated, moving particles too much or too little. So it will impact the reconstruction efficiency. And of course, eventually it can generate, introduce bias as well. But I think rule of thumb, most of people will agree is as long as B is within about 10% correct, and likewise, F is about within like 10% correct, the reconstruction is fairly stable against those assumptions.
Okay, thank you.
Okay, so let me move on. A very short beginner's guide. It's really not guide, but Okay, so how do we extract the BAO feature? Again, right, we cannot use all the, unless we want to do field level inference, we can't use tens of millions of galaxy positions and find the best fit at cosmology. So we do data contraction using, especially we do further data contraction. So for BAO, we use monopole and quadrupole of correlation function and monopole and quadrupole of the power spectrum. We used to see a hexadecapole. We used to use hexadecapole, but hexadecapole was harder to model. And also it's very noisy. And we concluded hexadecapole does not contribute too much to the information. So the most of the current BAO analysis, we use monopole and quadrupole. So I want to just show using a diagram I made a long time ago, why do we want to isolate the BAO and why BAO is a very good standard ruler. So in this, in this plot, let's assume the cyan range is the observable range. So we have a maximum, minimum Kmax, maximum scale we can observe. We have a minimum scale, the maximum Kmax we can trust based on our model. And so this cyan window is observable window. So if our power spectrum is a really simple power law, the RST the effect such as due to redshift space distortions, which introduces angle-dependent anisotropy, would be indistinguishable from dilations due to distances. So these two are not structurally, but almost degenerate between the two. But of course, if you have a distinct signature, right, the two can be clearly distinguished. So in our case, the power spectrum, of course, is not the simple power law, but it has a slow rollover. So in fact, actually, we can do the standard ruler test with the shape of the power spectrum. But doing so really requires careful work because nonlinearity alters this shape on small scales. We need a really nice model, the sophisticated model to the model such effect. But if we have a BAO feature, the two are clearly distinguishable. The amplitude distortion versus the horizontal the dilation would be distinguishable. Okay, so because of this, although the power spectrum has a lot of information, even more than BAO, as Stephen has talked about, we are doing the BAO only fitting because this is the most robust, conservative the information of the expansion history. So for the BAO analysis, we really trying to remove information, any information beyond the BAO as much as we can. So that is really the first principle of the BAO analysis. So sorry for a more complicated the equation, just too much detail here, but general, the BAO fitting formula looks like this. The shape has changed slightly, but the spirit is the same. So what we are trying to do is with the damped BAO, within the damped BAO, we prepare damped BAO, and we introduce nuisance parameters, or these higher order bias terms, or the additional terms due to nonlinearity, various nonlinearities. It does not matter to the BAO analysis. So we introduce enough nuisance parameter to observe all these effects. And the key element here is this part. So we are dilating the damped BAO left to right until it matches the observed BAO feature. So measuring this shift is just simply the BAO analysis. Okay. So I did this. So how does it actually appear, show up in the clustering monopole and quadrupole statistics? So this is a plot from Nikhil and Martin's 2008 paper, and here this is a monopole, and this is a quadrupole, and of course when alpha iso changes, the peak here will change to left to right. But this plot is simulating the effect of anisotropy. So if we assumed incorrect reference cosmology, such that alpha AP is different from unity, let's say that's warping, what would that do to the quadrupole? So as you can see, it impacts the monopole a little bit, but in the quadrupole, the greater anisotropy shows up in the quadrupole as a more prominent BAO peak that's shifted from the monopole BAO peak. So our BAO fitting in the monopole and quadrupole is catching these features. So now if I compare that with the actual observation from the DR1, the DR1, this is a tracer, like combined tracer called LRG3 plus ELG1, and this BAO peak has been singled out here. The overall size of the BAO, the alpha iso, depends on, of course, location of this monopole peak. There we measured offset from unity to be, small, within a 0.2%. In the case of anisotropy, it shows up as a prominent peak in the quadrupole, which is shifted from the monopole. So as you can see, for this tracer, we do see some prominent peak in the quadrupole, right? That corresponds to alpha AP. That's about 2.6% offset from the unity. And this is another tracer LRG3 from the same data set. And again, the center of the monopole tells us the overall size of the BAO. And here you see the quadrupole doesn't have much, the feature here, which indeed is consistent with alpha AP we derived, which is less than 0.2%. So that's how the BAO peak will appear. A different ISO and anisotropy would appear in the correlation functions in the BAO analysis. Okay, any questions so far? Right, none. I'll move on. Okay. So how does BAO distances constrain cosmology? Right, so such as from DESI collaboration, so this is a DR2 results and as well as a DR1. So we measure the observed BAO scales as a function of loopback time. So these are the Hubble diagram. It's really observed scale relative to the reference scale. So if we use only the BAO measurements without any other external data, what do we really measure? We are measuring the observed size, which is dm over sound horizon scale RD. If I assume flat universe, if I write that down, it looks like this. DH is 1 over h. Again, this looks like this. So this Hubble diagram, if I connect this Hubble diagram with these quantities, you can see that without any other external data, and if we only assume the flat universe, the overall amplitude of the Hubble diagram up and down really constrain C over the combination of RD times H naught. And the shape of this Hubble diagram is constrained by omega matter. So therefore, using BAO alone, we cannot separate RD times H naught, and therefore we can't say directly about Hubble constant tension. These figures are also from DR2 paper, just showing different BAOs measured at different redshifts are constraining omega matter and H naught times RD with the different degeneracy directions. And as you can see, a low redshift trace BAO such as BGS constrain H naught times RD much better. And high redshift tracer like QSO constrains omega matter better. And when it comes all together, we breaks degeneracy and can put a tight constraint on omega matter and H naught times RD. Now, the purpose of this standard ruler test requires the sound horizon scale being calibrated. In order to have this scale calibrated, we need to know the baryon density and matter density, either through CMB, as I explained in the beginning, or from Big Bang nuclear synthesis. So once RD is calibrated, we are really measuring the absolute BAO scales, and therefore we are really measuring absolute distance scales. And finally, we can constrain Hubble constant and say something about the Hubble constant tension. The left panel is without the RD calibration, and right panel shows with RD calibration. So now we can constrain H naught with the BAO measurements. So of course, if we combine BAO with external data, we have a much more constraining power, so we can actually determine the time dependence of the expansion history. As you can, many of you have seen this and actually worked on this, showing or with the combination how well we can constrain the expansion, the equation of state of dark energy. So I'm not going to say too much about it. Okay, any more questions so far? Okay, then I'll just move to the final part. Yes?
No, I said everything looks good.
Okay, let me give you a brief summary of the history of the BAO measurements. But before that, I'd like to actually just show a few introduction. So what is a really standard ruler test using power spectrum? This is a power divided by 0 periods of reference power spectrum just to single out the BAO peak. And let's say the red error bars are the measurements. And of course, the red error bars are determined from the survey condition that I'm going to talk about. The standard ruler test is really asking how much we can shift. So it's a template fitting method, right? We use a linear power spectrum, damp with the expected amount of damping. And the question is really how much we can shift to the left to right. So the 5% shift in this case is if you within the error bar, if we can shift 5% to the left to right, that means it's a 5% constraint can be achieved for angular diameter distance and Hubble parameter. So you see that the BAO precision will directly depends on the signal to noise of the power spectrum. In this case, the noise of the power to the signal of the power is proportional to the observed power spectrum, which is a combination of power spectrum plus such as a shot noise, divided by the signal, and the noise decreases by square root of number of modes, which strictly depends on V survey. So that's how we calculate the error for the Gaussian random density field, how we calculate the error on the power spectrum. And for the BAO case, because this directly propagates to the BAO precision, we can actually make a small modification and write the BAO error to the signal in this way. The only thing I changed is because now our signal is damped, the wiggle, so we can include the propagator term here. My apologies for changing C to C squared here and there. It's because notation evolved a little bit. So this damped BAO with observed power, which is reduced by square root of a V survey. So this works great for forecasting the BAO, the precision. As a caveat, the BAO surveys are usually designed such that P is greater than noise by about factor of 3 around the BAO scale. So this is to enable the reconstruction, efficient reconstruction. How well does that work? So this is the figure that I took from Yunder's paper. So this term is basically reflecting, right, this part. And you see the dashed line is a simple recipe based on signal to noise weighted survey volume called V effective. And that the point correspond to actual survey BAO measurements. You see that the forecasting BAO precision is really straightforward. It's easy. So I singled out a few the BAO features from the past surveys. So this is our first BAO detection in 2005 from SDSS. So there are BAO detections from SDSS and also 2DF survey. And for this SDSS, the effective volume at this time was 0.72 gigaparsec cube. And the BAO measurements was between 0.16 to 0.47. And the precision associated with the BAO scale was 4%, and it was a 3.4 sigma detection. Okay, and this is one of the BAO feature we in 2017 from the BOSS survey from Ashley's paper, and you see it has been much more strengthened. And in this specific example, the detection significance is now greater than 8 sigma. And the aggregate precision of entire BOSS and eBOSS is 0.6%. So within about 12 years, the precision is from 4% to 0.6%. The most recent BAO measurements from DEGI-DR2, we have 7 BAO measurements, and this is our best one. Altogether, now the aggregate precision is 0.28%, and the effective survey volume is 42 compared to 0.72. And in this specific case, it's a 15 sigma detection of the BAO peak. All right, so this is a compilation of the BAO measurements that's made by Ashley. So I will give you a few seconds for you to take a look at. Okay, so let me give a just chronological summary, incomplete summary. So before 2005, there were a lots of theoretical numerical studies of the BAO physics. And around 2003, there was the first WMAP result released. And 2005 is the first BAO detection with SDSS and 2DF at about 3 sigma. In 2007, we developed the reconstruction method, which was tested with the simulations. In 2012, we actually first applied the density field reconstruction on DR7. And also this is a time when we first conducted the two-dimensional analysis, the two-dimensional standard ruler test. Before that, we were doing only one-dimensional standard ruler. In 2012, both DR9 is the first time we actually achieved the 5 sigma BAO detection. In 2013, the first Planck result was released. In 2015, it's the first time we achieved 1% BAO measurements using both DR11. And 2012-21, I'm skipping steps in between. It's when the EBOS and BOS was complete with the DR16 with the aggregate BAO precision of 0.6%. And 2014, the last April, and we showed 1 year of DEGI data is better than 24 years, 2 decades of the previous BAO surveys. And we also presented a strong hint for time-evolving dark energy. And this year in March, DEGI DR2 result was released with 2.4 times more signal to noise compared to DR1. I omitted the wiggle Z and DES, which are also important elements, important points along the history of the BAO measurements. So my talk is done, and just to conclude, what if, I heard these questions, people asking these questions to me and others, what if, as we collect more data, if it just turned out to be the universe is even more perfectly lambda CDM, then what? So this was being asked when we are preparing for before EBOS and DEGI, and this is what I hear in my colloquium talks. With the DEGI now, we have an answer to this. Now we are beginning to find deviation. So I think this is a very exciting time, not just for BAO, for all different sciences using large-scale structure survey. With the DEGI, perhaps DEGI 2, and Euclid, Roma, and DSLST, I think this is going to be a super exciting time. Thank you.